Hello everyone. We're winding down the year, so today we're going to start looking at limits. First, let's define a limit. If f of x becomes arbitrarily close to a unique number L as x approaches c from either side, then the limit of f of x as x approaches c is going to be L. And it's written in this form. So the limit of f of x as x approaches c equals L. The limit can also be shown that f of x will approach L as x approaches c. The first method we want to go over is approximation. And this is going to be your fail-safe method. We're finding the limit of this function as x approaches 0. Well, if we plug in 0 here, so I'll put f of 0, we would get 0 over square root of 1 plus 0 minus 1. So we would get 0 over 0, which is undefined. So as we're coming from the left, you can see the values are 1.99499, and then they go up to 1.9995. And coming from the right, from the positive, when x equals 0.01, we get 2.00499. And as we get closer to 0, you can see that the value gets very, very close to 2. So as x approaches 0 from the left and the right side, it is getting closer to 2, so we can say that the limit is 2. When we look at the graph of the function, we can see that it will have a hole when x equals 0 because it's undefined. You can see that the y is getting very, very close to 2. There are several situations where limits do not exist. We can use the acronym DNE for does not exist. The first is when you have a function that approaches a different number from the right side than it approaches from the left side. So if we're looking at this function, absolute value of x over x, as x approaches 0 from the left, from the negative, you could see f of x is equal to -1. And as x approaches 0 from the right, we can see that f of x equals 1. Because it's inconsistent, we have to say that the limit does not exist. Another situation where the limit does not exist is when f of x increases or decreases without bound as x approaches c. As we approach 0, you can see that it's getting increasingly higher. Since it does not approach a unique real number L, the limit does not exist. The third scenario is when f of x oscillates between two fixed values. As x approaches 0, it's oscillating, so it goes from -1, 1, -1, and then from the right, 1, -1, and 1. Because it's oscillating, we have to say that this limit does not exist. Let's go over the basic properties of limits and direct substitution. So direct substitution is the most common and easiest method to determine the limit of a function. So whenever possible, try to use direct substitution. Now we're going to use direct substitution to verify these basic limits. So the first one is the limit of a constant function. So the limit of b as x approaches c will always be b. So for the example, the limit of 2 as x approaches -pi is also going to be 2. And you can see that -pi really doesn't make a difference here because whatever x value we have, y will always equal 2. Now let's look at the limit of the identity function. The limit of x as x approaches c will be equal to c. So here we have the limit of x as x approaches a, and you can see that the value is getting close to a. If we're going to find the limit of x as x approaches 5, well, it would be 5. Let's consider the power function. The limit of x to the nth power as x approaches c will equal c to the nth power. So if we have the quadratic here, the limit of x squared as x approaches 4, well, that'll just be 4 squared, which is 16. Let's look at the radical functions. So if we have the limit of the nth root of x as x approaches c will be the nth root of c. So here we have the square root function, and we want to find the limit of the square root of x as x approaches 4. And you can see it's going to be approaching 2, so the limit will be 2. Here are 5 more properties of limits, and oftentimes they'll be called the limit laws. So if we know the limit of f of x when x approaches c equals L, and limit of g of x as x approaches c equals k. So if we're going to find the limit of b times f of x, well, that would just be b times L. If we're finding the sum or difference, so find that limit of f of x plus g of x, well, that would be L plus k. And if we were finding the difference, f of x minus g of x would just be L minus k. The product law, the limit of f of x times g of x would just equal Lk. The quotient law, the limit of f of x divided by g of x would be L over k. And the power law, the limit of f of x raised to the nth power is going to equal L to the n. Okay, so let's determine the following using the graphs of f of x and g of x. So the first one is looking at f of x as x approaches 1. So we can see as x approaches 1, from the right or the left, it'll be equal to 2. For the next problem, what's g of x as x approaches 2? So coming from the left, we're getting very close to 2, but coming from the right, we're getting very close to 3. So this is a situation where they're approaching different numbers. So remember, whenever that happens, the limit does not exist. Now for C, find the limit of f of x plus g of x as x approaches 0. So when we look at f of x as x approaches 0, we're getting very close to 1. And for g of x, as we approach 0, well, the y is 0. So it'll just equal 1. Now let's look at D. Find the limit of f of x times g of x as x approaches 1. So for f of x, remember we said that as x approaches 1, we're getting very close to 2. And as x approaches 1 for g of x, we're getting very close to 1. So that product will just be 2. For E, let's find the limit of f of x plus g of x as x approaches 1. So remember we found that f of x would be 2, g of x would be 1, so that'll be 3. Now let's look at the last one. Find the limit of g of x over f of x as x approaches 3. As we're approaching 3 on g of x, the limit is 0. And for f of x, as we're approaching 3, the limit is -2. So 0 divided by -2 is just 0. Finding the limits of polynomial rational functions is actually quite easy using direct substitution. So if we're finding the limit of p of x as x approaches c, well, we just have to substitute x with c. If we have a rational function, we can use direct substitution, but just need to make sure that that value c does not make the denominator equal to 0. So let's look at these examples. Find the limit of x squared minus 3x plus 7 as x approaches 3. So we're going to substitute 3 for x. So we have 3 squared minus 3 times 3 plus 7. So we can easily do that, and we'll just get 7. For b, we have a rational function, and we can see from the denominator that x cannot equal 0. And it's good because we're looking for the limit as x approaches 3. So we can just substitute here. So 3 squared minus 3 times 3 plus 7 over 3. And remember, we just simplified that, so that'll be 7 over 3. Well, that's it for today. We'll go over more problems together in class.